Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications, Chapter 4, Climate Matrices and Linear Algebra. In this section, we will dive deep into details about the SVD analysis of the Southern Oscillation Index, namely SOI. For more information on SVD analysis, watch the linked video. Let's begin by downloading the pressure data for Tahiti from the following URL. The first thing that we will be doing in this video is plotting the SOI, which is the Southern Oscillation Index, and the standardized SLP data at Darwin and Tahiti. We are first going to set up the file path. You are going to name a variable file for easier access. Then we are going to go into that NumPy package and using the load text function. This file is a text document, so we do need to use that load text function. This skip rows parameter just notifies Python that we are not going to be skipping rows in order to read this text file. We are going to call this loaded text file PTA. Then we are going to redefine PTA by using the NumPy reshape function on that newly loaded data with all the rows, but we are going to skip the first column of data, which has a 0 index, and this slice simply means that we are going to take the second column of data through the rest of the columns. This reshape function is necessary for this specific text file just because of the way we know that it is set up upon loading it. Next, we are going to make an array of years for our x-axis. We are going to do that by using the NumPy linspace. We are going to have our first parameter as 1951, our second parameter as 2016, and then our third parameter is going to be what do you want your step to be. This calculation that is highlighted is our desired step, so then we can get monthly steps between the years 1951 and 2016. Next, let us go into setting up our figure. We're going to be setting up our figure using matplotlib figure function, specifying our fig size. We are going to add our data to the plot. We're going to use our time variable, which is that uniform sequence between 1951 and 2016 as our x variable, and our PTA variable as our y variable. We're going to use a color red. Then we are going to appropriately label with an X label, a Y label, and a title. Don't forget to wrap your block in that PLT show. Once you run this block, you will get the standardized Tahiti SLP anomalies. That is given by year, and we are looking at the differences in pressure. Next, we are going to download a different type of pressure data from the URL. We are going to upload and set up that data using that load text method. Once again, we are going to reshape that variable, getting rid of that first column and reshaping it to the second through last columns. And this data will be named PDA. We're going to just plot it using the same method used above, that PLT figure, setting up our figure first, then adding our data using that x time sequence as our x variable, and our PDA as our y variable. We're going to use color blue for this plot. We're going to rename X, Y, and our title labels, and don't forget to wrap it in a PLT show. We do get the standardized Darwin SLP anomalies dictated by year, and we are showing the pressure differences between all of these years. Next, we will be plotting the SOI index. Just remember that SOI is the Southern Oscillation Index. We're going to start off by setting up our figure. We are going to be setting up two different types of subplots, namely our fig and our SOI variable. Both of these are going to equal that subplot's function in the matplot library. First, we are going to be using the SOI figure that we just defined to plot our time variable with the difference between the Tahiti data and the Darwin data. We're going to set this X label and set Y label for our SOI plot. Notice how this is a set underscore X label function rather than just an X label function as we used above. This notation is because we are going to be plotting on two different axes in our plot. Next, we are going to make a left Y axis. We are going to do so by using that SOI figure and the twin Y function. This function simply will replicate our Y axis that we already have onto the left axis. We are going to name this AX2. We are going to plot the data against the difference between Darwin and Tahiti standardized SLP data. So we're going to use that AX2 variable we just defined, and we are going to plot our X time versus our difference. And this color is black. We're going to set our X label as year for that left axis. Now we are going to mirror our X-axis for the difference of data. Rather than using the twin Y function, we are going to use the twin X function and name this axis AX3. We're going to be plotting the same data that we have plotted in the SOI figure and the AX2 figure, with that X time variable as our X and then the difference as our Y variable. We are going to keep our color the same. Then we will set our Y label on that AX3 figure. We're going to add just a little bit of text because we have axes on all four sides of our plot. We are just going to use this text function as our title. Once we go ahead and run this block, we do get this plot to pop up. We can see that we do have our text, our desired text, on the inside of our plot. We can see that we have an SOI index on both the right and the left sides of our plot. We also have year variables on the top and the bottom of our plot. These were made using that twin X function and that twin Y function. We simply did this just for easier approximation of certain SOI indexes with certain years. Next, we are going to look at CSOI and AMO time series comparison. Let's start off by preparing our variables. We're going to let that Southern Oscillation Index, SOI, equal the difference between the Tahiti and Darwin data. Next, we are going to define a CNEG SOI, SNG SOI, as the negative SOI cumulative sum. So this function that is highlighted will take the cumulative sums of the negative SOI index that we created in the line previous to this one. We need to load our AMO data next. We are going to use that load text function once again with our file path that is highlighted. You can download this AMO data from the URL that was shown previously. We do have to specify which AMO data we are going to be using. The AMO data that we are going to be using is dictated with this slice, meaning we are going to use all rows but only columns 1 through 13. Next, we are going to transpose that AMO data from that slice using this .t notation. Once we transpose that AMO data, we are going to use a flatten function in order to make it into a single vector of data. You can read about the documentation of the flatten function to find out what this f means. There are other parameters that you can put in the flatten function in order to flatten your matrices of data in certain orders. Next, we are going to set up our figures. We have Fig 1 and Ax 1 being set up as our subplots to begin with. We are going to have our AX1 variable set as year and our Y variable set as the negative CSOI index. Next, we're going to add our data to our AX1 figure using that time sequence that we created above with that CNEG SOI data that we created from the negative SOI cumulative sums. This plot is going to have the color purple, and we are going to label it CSOI in our legend. Next, I'm going to create a second axis that shares the same x-axis. We are going to name it AX2, and we are using that twin x function with our AX1 figure. We need to set our labels for our new axis, so we're going to set our Y label as the AMO index for that AX2 figure. Then we are going to be plotting our time sequence against the AMO data that we retrieved from that URL. This plot is going to have the color green and the label AMO. We are going to set these legends. In order for both our AX1 legend and our AX2 legend to appear, we do need to run the legend function on both. I do specify a preferred location for each of these legends just so then they do not overlap. Next, we're going to use that figure that we set up right at the beginning of this block, and we're going to use the tight layout method. This just allows us to see the full view of the right Y label. Not forgetting to wrap our block in that PLT show. we do get this plot to appear. We have the negative Csoi index on the left side of our plot, which is dictated by the purple line that you see. On our right y-axis, we have the AMO index, described by the green line that you see. We have the same years going on for both of these y-axes. This allows us to see the comparison between our negative Csoi index and our AMO index across the same years, which is really important, especially in climate science. Next, we are going to be looking at the weighted SOI computed by the SVD method. First, we need to yield the transpose of our data. We are going to transpose our Tahiti data and our Darwin data. These transposes are simply made with that .t notation. Next, I'm going to create an array of arrays and name it PTADA. We are going to be creating that PTADA variable by just wrapping our previously defined variables in an outer array, thus creating an array of arrays. Next, we are going to compute the SVD of that PTADA. We are going to name the outputs from the SVD in the following way. We have SVD PT underscore U, SVD PTD underscore S, and SVD PTD underscore VH. And we're going to be defining those variables using that NumPy linear algebra package, accessing that SVD function on our PTADA data created above. We do dictate that these are not full matrices, so it will take out the information that we will not be using in these results. We're going to verify our SVD just for clarification purposes, and this is going to be named Recon TADA. In order to verify our SVD, we do need to set up a few dot products. So this computation that is highlighted will compute the dot product between the SVD PTD underscore U and the diagonal version of the SVD PTD underscore S, and finally computing the dot product with the SVD PTD underscore VH. We are going to compute the error of our calculations. This is always a good idea when you're using any climate science data. We are going to do SVD error is equal to our data minus our Recon TADA verified SVD variable that we just created. We're going to find the maximum error that is present in that SVD computation using that SVD error vector and finding the max from that vector. We do get a max error of 8.88 e to the negative 16. This number is very, very close to 0, thus ensuring that our SVD was computed correctly. If we wanted to find the minimum error, we just have to use that min method on our SVD error vector, and we do get a minimum error seen in out 33 as negative 2.66 e to the negative 15. This number is also very close to 0. Next, I need to gather the appropriate variables. I'm going to be doing so by naming our dd variable equaling to our diagonal version of the SVD ptd underscore s that was computed in the SVD computation in inline 32. We're going to be naming our UU variable as the SVD ptd underscore u, and our VV variable as the SVD ptd underscore VH. We are just redefining these three variables for easier access, so we do not need to repeat these long variable names in our calculations. We're going to set up a time array once again, spanning from 1951 to 2016, and we are going to get monthly increments from this calculation. Next, we are going to compute the WSOI1 for our desired plotting. We're going to do that by accessing the 0th row, 0th column element of our D matrix. And we are going to multiply this element by our V matrix, accessing the first row, all columns. We will receive a vector of elements as our WSOI1 variable after making this computation. To plot our WSOI1 variable, we're going to set up that figure. We're going to use X time and our WSOI1 variables, and we are going to plot in black. We're going to label our X label our Y label, and we are also going to add some text. Once we run that block of code, we do get this weighted SOI1 index plot. We can see that we have our weighted SOI1 on our y-axis with our years as our x-axis. Next, we are going to plot the weighted SOI2 index. In order to set up the weighted SOI2 index, we are going to access that D matrix, accessing the second row, second column entry. That is dictated by the 1-1 slice that is highlighted, because we know that the first element of a Python matrix is dictated with the 0-0 slice. We're going to multiply that entry by our V matrix, accessing that second row, all columns, and this calculation will be our weighted SOI2 index. We're going to prepare our figure, letting fig and WSOI equaling that matplotlib subplots function. We're going to be plotting our data on the WSOI figure. We're going to use our time sequence with our WSOI2 variable that we created above. This plot will have the color dark blue. We're going to set that X label, set that Y label. Then we are going to create the second instance of an axis using that twin y function that we have used a few times in this video. We're now going to be plotting on AX2 with our time variable and our WSOI2 variable. Once again, plotting in dark blue. We're going to set that X label and we're going to add a little bit of text just dictating what we are plotting, which is namely the weighted SOI2 index. Once we run this block of code, we do get this dark blue plot to appear. We can see that we have a twinning X label with year spanning across the top of our plot and the bottom of our plot with our weighted SOI2 index on our Y label. Next, we're going to plot the comparison between CWSOI1 and a smoothed AMO index. We're going to create this CWSOI1 variable by taking the cumulative sum of that weighted SOI1 that we created above. Next, we are going to prepare our figure. We have fig and plot equaling to the matplot library subplots. We're going to first plot the cumulative sums on the plot figure. We're going to use that time sequence as our X variable and that CWSOI1 as our Y variable. This plot will have a color black and its label is going to be CWSOI1 in the legend. We're going to set that X label and set that Y label for the plot figure. We now need to superimpose the CSOI time series onto the CWSOI1. We're going to find that negative cumulative sum between our PTA MONV variable minusing our PDA MONV. This is just the difference between the standardized Tahiti and Darwin data. Next, we're going to plot that time sequence against this newly defined variable CNEGSOI. This color is going to be purple, and we're going to label it with CSOI in the legend. We do need to mirror that x-axis using the twin x function. We're going to name this new plot AX2. Next, we are going to create a 24-month moving average of the monthly AMO index. We could do that by using this following to set our increment equal to 0, set our window size equal to 24. We are going to set up an empty array called moving averages that we will be appending to in our while loop. This while loop does create a 24-month moving average. Next, we are going to create a time sequence similar to the time sequences we have been using. Next, we are going to plot the moving averages that we made in the highlighted while function. We're going to plot these moving averages against that x time variable, and the color of this plot is going to be dark green. We're going to label it AMO index in our legend. Don't forget to set that Y label because we have so many different axes going on in this next plot, it is quite important to make sure you are setting all of your X labels and Y labels appropriately. We're going to set up that legend, one for our plot figure and another legend for our AX2 figure. Once again, using that type layout function so we can see all of the axis labels, wrapping this block of code with that PLT show, we do ensure that we get this plot to be printed. We can see that our black line is the CWSOI1. Our purple line is the CSOI, and our green is the AMO index. On our left y-axis, we have the cumulative weighted SOI1, and on our right y-axis, we have the smooth AMO index. Next, we are going to be plotting the cumulative WSOI2 and the CWSOI2. We're going to create the appropriate variables from that SVD computation. We're going to name our variables UU, SS, and VVH using that NumPy linear algebra module accessing the SVD function on our PTA DA data. We do dictate that we do not want full matrices in this highlighted line. Then we are going to rename some of these variables. We're going to name PC equaling to the matrix from our SVD computation that is defined as our VVH matrix. Next, we're going to label PC1 as that PC variable 0th row, which is going to be our first row by all columns, and our PC2 as that PC variable taking the second row all columns. We're going to now prepare our figure with that PLT figure function. We're going to make our time sequence. Then we are going to plot our time sequence against PC2 cumulative sum. The color of this plot is going to be blue, and we're going to label it principal component 2. Make sure you label your plot appropriately and not forgetting to wrap it in that PLT show. We do get this CWSOI2 index, the cumulative principal components, to appear. This concludes our section on SVD analysis of the Southern Oscillation Index. In the next video, we will continue with Chapter 4, but take a closer look at visualizations of the ENSO mode.